started. Okay, hey everybody, welcome to the the May meeting of the Baton Rouge Astronomical Society. Of course, Don, our president, is now up north in North Dakota. I think that's in North Dakota, South one of the Dakotas at Fort Abraham Lincoln for the summer. So you're stuck with me doing all the talking to start things off.
We're always stuck in that.
As with the way we've been doing the meetings and stuff, we are going to start with our guest speaker and get to the fun stuff first. And then we'll take like a 5-minute break or so, get some cookies and coffee and whatnot, and then we'll come back and do the businessy type stuff. And then if there are no clouds outside, once it's dark, we'll drag some telescopes out and some viewing and stuff. Without further ado, we are honored to have with us this evening Dr. Param Singh from LSU Department of Physics Astronomy, and he is going to give us a presentation.
So just to close up, like I want to thank Madam, thank everyone for coming up. Thanks so much for giving the opportunity. Some of you might have looked at this talk earlier in different formats. I just want to introduce myself. My name is Param Singh. I did my PhD from India from an Inter-University Center for Astronomy and Astrophysics. I was probably the most hated guy there because I was not doing astronomy, but I was doing theory. I was mostly interested in black holes and Big Bang. This was a great place to do astrophysics and astronomy and gravity. And then I went for a postdoc at Penn State for a couple of years. That is where the work which I'm going to show you started. And then I went for a postdoc in Caribbean Institute in Canada, and I joined LSU 15 years ago. And I have my group there, and it's one of the leading groups of the world of some of the questions we'll be talking about. So the results I'm going to show you, which are towards the end of the talk, these originated first from the work which I was doing with my mentor in Penn State back in almost 20 years ago. But these have been verified by various international groups, and various people have worked on it. So it's not like I cannot specify this is my result and so on.
I'm trying to see what's going on here. They must have timed out and gone to sleep.
And please feel free to pause me in the middle, and if you have questions, I don't want to lose any of you. The way I have structured the talk is, this is an extremely mathematical topic. Probably some of the parts I myself do not understand fully, and that's why I have no equation to talk. I'm going to just talk a bit about history, the way thoughts have developed, and what we can learn from that history to come to probably some new or radical ideas in gravity. Okay, so my research is from the International Science Foundation since I joined LSU. The title of the talk is Quantum Nature of the Big Bang. It's a loaded title. I'll go slowly. What do we actually mean by quantum nature? We all know what is quantum theory, but how did those ideas develop? What is the Big Bang? And so on. And this scientific American article, about a decade ago, this we mentioned about this big bounce, which is essentially the result which my group found starting from when we were in Penn State. And the idea, the main result you can already see, instead of a Big Bang, the theories which I'm working on, which try to take us beyond Einstein's theories. These theories are not finished yet, and you have to take some of these results with a grain of salt, maybe a mountain of salt at some point. But the idea is that if these theories are true, then the universe didn't start from a Big Bang, but had a contracting universe on the other side, of the universe is cyclical and so on, but non-singular. The way it differs from the previous ideas is that most of the ideas assume that the Big Bang singularity is resolved, whereas in this framework, you can show mathematically and computationally using high-performance computers that the singularities are genuinely resolved. How does it tie up to the quantum nature? Because we will be looking at the atoms of space-time, not just the atoms which make materials, but the atoms which make space-time. So that's where I'm going to start. So this is the outline of my talk. We'll talk first about the quantum nature of matter, the dynamical nature of gravity, and how it leads us to the Big Bang. Then we'll talk about what's the marriage of quantum and gravity, and this is the most related marriage for theoretical physics and astronomers and astrophysicists from last 80, 90 years, and it has not happened so far. And probably it will never happen, but we have been trying to make this couple together. And obviously it probably tells us that we don't understand perhaps some parts of both of quantum and gravity yet fully. And then what if suppose such marriage happens, at least in some models, which are models which means models very similar to like what we build here in this observatory. Like my son, when he used to come here like a couple of years ago, he would make these rocket models in the summer camps and so on. Those models, you can think of these as we are making those models. Obviously, those small rockets which gets built here, they cannot go to the moon. But the principles, underlying principles are very similar. Like it's just like how do you scale things, how do you add more complexity, how do you make a bigger rocket more successful. So that is what I'm going to talk about. Certainly, we do not have a complete picture of the marriage of quantum and gravity, but we have enough confidence, thanks to mathematics, which has been developed over the last 30 years, and thanks to the checks and boxes we have checked and so on, that marriage should work at least in certain situations. And what do we learn from those situations? Thankfully, like that marriage, when it works, it can tell us about the Big Bang, and it can tell us about the black hole. Very exotic phenomena by itself, but I won't talk about black holes in this talk. So let's look at why do we need and what we need. So this is roughly the history of the universe which we know so far, thanks to precision astronomical experiments, that our universe is probably 13.7 billion years old. Yes, we do not understand various things. We do not understand what is dark matter. We do not understand what is dark energy. But we do understand there was no dark energy almost 13.7 billion years ago, and the dark energy is more a recent phenomenon, and probably it's going to stay like this. And how do we know all this? Because of the cosmic microwave background, which was accidentally discovered, and there is again like a long story behind that, starting from Sputnik and so on, and how did we discover it, how did Americans discover this. But the idea is that thanks to these precise experiments, we have a great knowledge about and great confidence about the knowledge we have from just after the Big Bang on how the inflation probably would have started. We don't know what causes inflation exactly, except some mathematical idea, and what exactly is inflation. But we know that there is an inflationary paradigm, and when that inflation ended, then the hot Big Bang happened, which is called the particle formation happened. And then when those protons were formed and they cooled down, then the simplest elements formed. When they cooled down, then the first stars formed. And then at some point here, the cosmic microwave background, which we see in the universe, was ejected out between. That's a snapshot of the history of the universe at that time. First stars formed, galaxies formed, and we are living somewhere here. The mystery is like what exactly happened here. So, like what happened here, and was there a space-time beyond this space, beyond this, and what caused the initial conditions of it? What was the birth of the universe? Now we may say like, why do we want to ask these questions? Because unless we answer this question, our theories are incomplete. It's not that this is just a question of curiosity. The problem is that whichever theory you may use to describe the expansion of the universe or the behavior of the universe, that theory breaks down here. Any theory. If you want to work with Einstein's theory, that breaks down. If you do not want to work with Einstein's theory, but a modified version of Einstein's theory, that also breaks down. Every theory which we know classically, it breaks down. So something fundamentally is missing here. But whenever theories have broken down in physics, it has always led to a new revolution in physics. Something completely radical has emerged. And that is what has been driving the research in what is called as quantization of gravity, or marriage of gravity and quantum from 1930s. Like Einstein also worked on it in his last stage. Schrodinger also worked on it. Like almost everyone has worked on it and contributed different ideas. But as I will try to show you, this is such a complex and difficult problem. And probably like if in the talk, like you, if I can only make it appreciate that, yes, this is a tough problem and why it's not solvable, I think like probably have achieved some of my goals. So let's go back in time. Let's go look at the early attempts. It's not that we are the first ones to answer these questions from 1930s. These have been long-standing questions. Like you can go back to 900 BC or something like that. Like Vedic philosophers from India at that time, they have these speculative ideas which are obviously feels foolish and wrong now. That there is a big turtle. That big turtle has four elephants in four different directions, which is holding this earth on top of it. There's probably an ocean there, and then this turtle is actually sitting on a snake. I have not fully understood like what this snake actually means, because in Indian philosophy, like philosophy and mythology, they are so much interlinked and so on. Uh, but like this snake also reflects about probably a cyclic evolution or a cyclic universe. So, similarly, like earlier attempts of the pre-Socratic Greek philosophers, Thales and Maximenes, for them like the water and air were the most primary elements. Like Thales imagined that there's a platter which is floating on a big ocean, and his school later on is one of his pupils, like an Maximenes, that he thought like the more fundamental stuff is air, and basically they compare water and air together, they can essentially produce all of the things. You also see these elements in various philosophies about fire, earth, water, and air, that everything is composed of them, including like the Greek philosophers and again like Indian philosophers and so on. But what I want to say is that these were the primary ideas at that time. Like this is what the matter is made up of. And we will see like the journey from matter to space and time is very much interlinked. That is why I want to like spend some time on the matter part, because that is where our historical references. Okay, then again the ideas of atoms came up, like going back to 900 BC, 800 BC, like again like Indian philosophers were talking about particles which are probably too small, you can't see, they will clump together and then they will form substances. And then there were also some schools which they said like these, they didn't call the word atom, obviously that's a Greek word, but like equivalent to that, what they call as Paramanu, like they will form triads and they will form dyads, like, and then they will form these substances which you can see. Like the origins of the molecular theory, obviously they didn't know anything about the covalent bonding and so on. The ideas were there, speculative ideas, all these are speculative ideas, nothing mathematical here. And similarly, like in the Greek school, like it was proposed that the matter is composed of all these indivisible matter and particles which are called atoms. And at that time, like there was a great confluence starting like from the Greece to the Mesopotamia and Egypt and India. Like I won't be surprised if all of these ideas were interlinked and there was a cross exchange of knowledge at that time. But from these atoms of matter, which was the idea which was already there, the revolutionary part is that these are the things we could not see. Like the philosophers at that time, they were making really radical proposals. Now it seems like a child's game. Yeah, of course we have seen. I have never seen an atom if I did my naked eye. So I just believe that people have seen, right? But like we know that atomic theory is true, and we know that the standard model of particle physics is extremely successful. But like imagine like the kind of guts which are needed at that time by these philosophers in 900 BC, 800 BC to 400 BC, talk about things, and probably they were all being labeled as crackpots at that time, but they were going in the right direction. This was the foundation of the philosophy of science at that time. And I think the biggest leap came from the Aristotelian ideas, again like based on like again partly because of this religious or spiritual reasons, that Earth is the center of the universe and all the stars move in perfect circles. And who will deny it? Like if you take a snapshot, if they, and you will see like all the stars are moving in circles around the Earth. This is just the living evidence, and this which was in front of them. And well, then it was noted that well, not all stars, not all planets move in really great circles and some wander around. That is why they were called planets. And that is why that actually led to the birth of astrology, because it meant that maybe Jupiter, which is retrograde at some point, or Mars or Saturn, they have enough power to disobey the heavenly Earth, which is the center of the universe. And if they can disobey the going in perfect circles, probably they will also influence our lives. So the birth of astrology is actually tied to the way like these variations are there in the circular order. But I think the most important thing, which will come back, which we will touch upon when we talk about Galileo, is that the Aristotelian school uh, talked about motion and motion about projectiles. And projectiles are very important objects to be studied because they are like war machines of that time. If you throw some, even if you're throwing rocks or something else or heavy objects, these are projectile motions. And when these were asked about, when the Aristotelian philosophers were asked about these projectile motions and how to describe them, the answer was that, well, the projectile motion you see in particular has two kinds of motion. There's a natural motion, and then there's an unnatural motion, which is power. The natural motion is when the projectile is falling towards Earth. And then they were asked why objects fall towards Earth, because Earth is the center of the universe. Earth takes everything. Earth absorbs everything. So that is why things fall towards it. There was no gravity talk at that time. But Earth is the center. Things fall towards Earth. And why do the projectiles move up? Well, maybe by the force of wind, they move up, or somebody has to push them in the sky to move up. And then these were the kind of questions they were wondering about. The Aristotelian philosophers were more interested in why do the objects move in circles? They move in circles, yes. Why do the planets wander? Because they have some sort of a spiritual power to influence, or great mystic power to influence probably even the life on Earth. But if somebody asks, well, I want to understand if I throw a projectile with a particular angle or a particular speed, and I want to see like how far it goes up, and then what velocity it comes down. These are the standard problems found in the 9th grade, or 10th, or like physics 1 or physics 2, which you do in high school. And these are very important problems. The Aristotelian school will tell us you should not be asking such useless and mundane questions because they have nothing to do with fundamentals of philosophy. An object goes up and comes down. The biggest thing is that it goes up to the center of the universe, and objects come down. With what velocity it comes down, and so on. These are all trivial questions. You should not waste your time with that. So these were not asked, but these will be the primary questions which led to Galileo's discoveries. So I think like this is what I was mentioning earlier. This is where the intellectual snobbery shows up many times in science. That some questions are not worth studying. Okay, so it's not that they were not rebels, like they were rebels both in Greece and towards the Eastern schools. That Aristarchus of Samos, like he was the first one actually to give a heliocentric model, with the central fire as nothing but sun. And I have worked in almost like 580, like he argued that Earth is not just fixed, Earth is rotating, and so on. But these rebels, the force of the Aristotelian thought was so grand and so obvious that no one could touch. Like these rebels were treated as basically like, okay, these are rebels, these are interesting ideas, interesting observations, but this is not the mainstream physics of that time or astronomy. So it's based on these, like many years passed, almost thousand years passed, and I think one of the main folks we can give a lot of credit to was Copernicus, who was actually asked by Pope to fix the calendar. He was working on the calendar, but most of the time he was spending on his book, which was published in his last days, in which he figured out that universe was, even though he assumed universe was finite, and he was the main person who gave the heliocentric model that there are the stars which and planets and Earth, which planets and Earth move around Sun, and Sun is one kind of star. It was published in his last days. He had a lot of Pope Paul III was his friend, a very dear friend. So no one could have touched Copernicus. Well, a very similar scenario was not possible for Bruno. And when he tried to advocate Copernicus' ideas, Bruno was actually burned alive. So a lot of politics was also going on at that time to suppress science. However, I think one of the major discoveries was done by Galileo, which shook the foundations of Aristotelian physics. It's not that the rebels had not come, but they had come and they had gone. But the Aristotelian ideas were so obvious that people thought, well, anyone disputing them has to be completely crazy. For example, suppose like you have a lighter puff cotton and you have this pointer and you throw them from the same height. It's obvious which one falls faster. But if you do this in vacuum, which obviously is not possible in the days of Aristotle or Galileo, then we'll see they will fall at the same time. So there was no principle of equivalence. The principle of equivalence, which was the cornerstone of Galileo's and Newtonian and Einsteinian philosophy, was discovered by Galileo. And the way Galileo proved that falling objects of different masses fall at the same time, we generally think that he was doing a lot of experiments on the Leaning Tower of Pisa, which he actually did. But most of his experiments were done in this inclined plane, which is actually in his museum in Italy. He was throwing the balls, he was measuring the velocities, similar kind of problems which Aristotle said these are the problems we should not be wasting your time on. So he was doing exactly those kind of problems which Aristotle prohibited or told people not to do. Don't waste your time on it. And using these inclined plane problems, he was able to figure out that yes, if I want to throw the balls also from the Leaning Tower of Pisa, I'll get the same result. That balls of different mass will fall at the same time. When he was doing that, people thought like he's doing some sort of tricks, maybe he's pushing something faster and holding something and so on. So people never believed him initially, but eventually they believed him. And the principle of equivalence was one of the first blows to the Aristotelian thought, because for the Aristotelian thought, it was very obvious: heavy object falls faster, lighter object like a cotton puff ball or a feather, they will fall later. The other thing which was extremely important, Jackie broke the back of the Aristotelian thought, was that Aristotle thought, and all the Greek astronomers who thought, that everything is perfect, everything is a circle. And that is why there is so much of emphasis on pi everywhere in mathematics and in philosophy and so on, because it's property of a circle. So circle is a perfect object and perfect figure. And that suns and moons and so on, they are all perfect objects which appear spherical, they are heavenly, nothing is wrong with them because they were created in heaven and so on. Galileo was able to figure out using this telescope, this very simple telescope here. I do not know the specifications of this telescope. This is the actual telescope he used. He was able to figure out that there are mountains on the moon, the sun has spots, and the motion of the bodies, heavenly bodies around the sun. It's not circular in many cases. So this was the second big blow to the Aristotelian ideas. I think like this was essentially where the cracks started appearing, and before that, with all the work which Copernicus had done, Bruno had done, Kepler had done, and many other folks were doing at the same time. But Galileo made many inventions, and his major contribution actually was to understand the dynamics of these new falling objects on inclined planes and curved planes and so on. So Newton, using those ideas, he was able to make a lot of progress, and like just talking about Newton's discoveries will take an entire hour by itself, so I'll just keep it in one slide. But one of his main ideas which we are interested in is that the planets move around the star in a space and time which acts like a fixed pattern. So in the Newtonian dynamics or Newtonian philosophy, for the first time we start talking about space and time as separate from matter. In the Aristotelian days, like space and time was seen again as a background in which the matter moves, but they were all part of the same picture. Newton tried to separate that. The planets move around stars in space and time, acting as a fixed background. So this is space. Let us say this is space. Let us say this is a particle or a star which is moving on it. So very similar to what we do in our daily life to understand the motion of things. These act like actors on a fixed state. So this is a fixed state. For example, this state, and like the particles moving on it, these are actors which are acting on this fixed state. This pointer is not influencing this fixed state. The fixed state remains the way it is. And then we can study the motion of rolling balls and the motion of any other things on this fixed state. But not everyone agreed with the notion of absolute space and time which is fixed. And one of the Newton's contemporaries, Leibniz, he advocated that, you see, like, what is actually, and Leibniz was more philosophical in that sense, and he emphasized the nature of relational dynamics, right? Things exist because they are related to others, or they are described and related to something else. Like, I can say, for the ideas are similar, like, if we ask, what is the time right now? Most of us will have a watch or a smartphone and we can look at that number. So this is the time right now. But how do we know that corresponds to the value of time for all of us? Because those our watches are synchronous, our cell phones are synchronous. But what does it mean? Again, like, that's because of the motion of the Earth, or how the Earth is spinning around its axis. And so it's all relational. It's not like the Earth has told us this is the time. But again, like, the motion of clocks, the motion of time, it's all really relational. It's because of the Earth's motion. Why the Earth's motion? Because of the way the solar system was formed and the Earth's angular momentum at that time. So all those things are related to each other. And we can, the one way to look at it is, if we will say like it's 8 o'clock, it's probably going, we know that it will be enough time to go out. The darkness has started and we can start setting our telescopes. It's not that the value of time gives us something really meaningful immediately. We don't. It's not like a quantity which we can drink or eat. It's just relational. It's just a memory, and not a memory thing, but it's more a conceptual thing which we use all the time. So something like that. So for time, it's more obvious. But what is not so obvious is that even the quantities in space and matter, they are similarly related to each other. Like defining, like, how do you define that a pointer exists at this point with certain weight? It's because of the weight of the objects around it. And this is what led to the Machian principle. Mach, which following Leibniz came up with this principle that the inertia of an object is determined by all other objects in the universe. Newton didn't like these ideas because these ideas were philosophically not appealing to his philosophy, and these were not based on absolute fixed background. But we will see that these ideas of Leibniz and Machian philosophy, these were the fundamental cornerstones for Einstein to make that leap. Again, like intellectual snobbery, even though Newton was perhaps the best genius, that stopped Newton to discover what Einstein could have probably discovered much before Einstein. Okay, so I'll take a leap here of a couple of hundred years. I'm going to skip like all the beautiful work of Maxwell and Michael Faraday and so on, because it's not so much relevant to gravity. But there was an end of old physics in the birth of the modern physics. And in the 1890s, in the beginning of 1890s, like Lord Kelvin, who played a fatherly role, very seminal role in thermodynamics, and Michelson, same Michelson Morley experiment came. Like they were talking about like future truths of physical science are to be looked for in the 6th place of decimals. Everything else is done. There is nothing left in physics and astronomy. Everything is finished. People should not be pursuing physics at all. Michelson, in fact, like, and Morley, like, who accompanied him, they were told when they were taking admission in the physics courses that you should not be doing physics. There is really nothing left. You won't get a job eventually. So, and Michelson, in fact, said that it seems probable that most of the grand underlying physics principles have been firmly established. So, people used to debate that, well, physics is going to anyway die. And one should be actually focusing on humanities, which is where the real progress is going to come. But in 1895, X-rays were discovered. In 1896, radioactivity was discovered. In 1897, Thomson discovered deflection of cathode rays, electric and magnetic field, and he had a great courage. So again, like something very similar to what we see in ancient Greek and Indian philosophers, to interpret the results in terms of existence of a new particle, which no one had thought of, an electron. And not only that, but to say like it's not only related to just my experiment. I propose that this electron is a fundamental particle for every atom. Like great courage which was needed. And then like in 1905, obviously like we had a photoelectric effect by Einstein. And in 1911, based on various of these ideas, Rutherford came up with his model of that. So physics was actually not dead. The old physics died, I would say. Like, this was the end of the old physics. The new revolution started from discovery of X-rays. Because discoveries of X-rays meant that we have now started seeing things indirectly which we thought will never exist. And similarly, radioactivity had no explanation. The discovery of electron had no explanation. photons had no explanation, but Einstein was able to explain like the phenomena which Planck was struggling with, and Rutherford was able to come up with an atom. So we go back full circle, we go back to an atom with the Rutherford, with the matter. But the Rutherford model had some problems, and to understand that, we can look at what the Rutherford model meant. Why? Like there was a positive charge in the middle, and the electrons were moving around this positive charge. And idea Rutherford had was that electrons will move around the positive charge in a very similar way as Earth moves around the sun. If you do that, it turns out that the electron will fall. There will be a tiny radio transmitter living only a microsecond life, and the electron will be completely unstable. So the questions arose. Well, what is actually wrong with this idea? It looks perfect. Like it's basically copying what happens, which we see in gravity. Earth is moving around sun. It has a stable orbit, and like yes, if you shoot an asteroid or something, it will probably spiral around and so on. But these atoms are stable; they are not decaying. So what's causing why why atom cannot be stable as the Earth-Sun system can be stable? This was the main question. So it meant that something was going on which was different, and this was realized by Niels Bohr. And his idea was that basically, like we cannot just assume that the physics which we see at the macroscopic scale between Earth and Sun is going to be valid exactly the same at the microscopic scale at the level of atoms. And he was able to conjecture, he postulated that electrons can only take specific energies, that the energies of the electron are not continuous. Electron cannot continuously lose the energy. Electron can only lose the energy in discrete energy levels. So he proposed his own model, which was stable, and it also was consistent with Einstein's earlier observations of what was photoelectric effect, and it was a great victory for Bohr's model, and he was able to make it consistent using Planck's constant, which is extremely small. So that is why we do not see those effects at the Earth-Sun system level, because Planck's constant is extremely small. But when you're probing when you're probing the microphysics, and you try to apply the same ideas, then you see that this Planck's constant plays a very important role. If this Planck's constant becomes zero, it's 10 to the power minus 34. But if it was exactly zero, atoms won't be stable. Like we won't have a universe like we know around us. No one will exist if this Planck's constant was zero. We'll have to come up with a very different explanation of the atomic nature of matter. If this Planck constant was very large, again, like we won't be living. Like the universe will be too fuzzy for us in a way. Like if this Planck's constant becomes, let us say, like of order 1, like you'll have to figure out where each of us are sitting. We'll become extremely fuzzy objects scattered throughout the universe. So one can say that, again, like a very mysterious, very small number, we are not looking at the 6 place of decimal. The physics was being done at 10 to the power minus 34 level, within 15 years or something. Okay, so what we learned so far, and this will be an important lesson for us as moving forward, that the microscopic world governed by the quantum theory is very different from the classical world. And instead of the trajectories, we have probabilities. So the earlier picture of the hydrogen atom, if one would make from the last Bohr, was that you will have a positive charge and you will have an electron which will be circling around. Bohr at that time in 1911 had not realized the power of what he had discovered. But after that, Heisenberg, Schrodinger, and Dirac, they figured out that the electron is not moving in a circular orbit. Actually, we can only talk about the probability distribution of the electron. Again, it's something we have not seen, something they had not seen at that time. But all these big leaps came just from the theoretical side. The mathematics was saying, from the Schrodinger equation, that the electron has to be in this, and the motion of the particle was dead forever. And we were talking about the fields now. Now we cannot say that quantum mechanics tells us there are particles and they are projected. The main lesson of quantum mechanics is that if this pointer was in the microscopic world, this will be a diffused wave packet. It will be, and I will have to do some measurements to figure out where this pointer is. Okay, so the picture, actually, real picture of the hydrogen atom looks something like this, which is very different from here, quantitatively, but still qualitatively, it has some similarities. So now let's try to go back to the gravity side. We have studied the quantum nature of matter. We started from like Yeah, there were various radical proposals. Slowly we uncovered various things. We stopped at the Newtonian side and then we took a small detour to the quantum side. In the Einsteinian ideas of gravity, the main contribution after the special relativity for 10 years Einstein when he was working on from 1905 to 1915-16, he figured out that gravity is actually a relational theory, very similar to what Machian and Leibniz ideas were. And in these ideas, the Machian principle and the principle of equivalence played a very important role. He made a big departure from the Newtonian idea, and the idea was that the gravity is not a force, like electric or magnetic force or any other force which we have seen. But the gravity is the dynamics of space and time itself. Planets do not move around stars because there is a force. You can think like that, but actually the reason planets move around stars because star bends the space and time in its neighborhood, and the motion of heavy objects affects this motion of space and time. The space and time is no longer a background state, but it changes as the actors move on. When I'm moving on this floor, if there were extremely precise measurements which were made, yes, I'm changing the structure of this floor as I'm moving. The gravitational background of this floor is changing. But that is an extremely small fact. But if a black hole or a neutron star will start moving on a space and time, it will change the space and time completely. That's a much more observable effect. So the main lesson was that space-time is no longer a background state. Space-time is a dynamical quantity. And the obvious example is here, like if you take a membrane, a rubber sheet, you put a heavy weight, and you throw, uh, throw like some sort of a small ball that will circle around, which gives us a glimpse of how the planets move around the sun. So, okay, so let's spend a bit of time on the expanding universe because we have discovered that we have talked about gravity, we have talked about Einstein's theory. We would like to understand what it has to do with the Big Bang. At a very similar time when Einstein gave his general relativity, Hubble discovered that the galaxies are moving away from each other, and the fainter the galaxy, the faster it will see from us. And this was extremely surprising news, including to Einstein, who believed that the universe is static, like very much like the Aristotelian idea or the Copernican idea. The universe is fixed and static. Okay, things are happening in the middle because of the relations between them, but everything is static, nothing is expanding. Then Friedman and Lemaitre, they found a solution of Einstein's theory of general relativity in which the universe was expanding. And Lemaitre described the initial state as premier atom. Again, he talked about there is some sort of an atom which is there, which is the initial condition of the universe. And the universe was extremely tiny of the size of the atom. Einstein obviously didn't like the idea, very similar to what Newton was doing with Leibniz and Mach. And Einstein didn't like this idea of what Friedman and Lemaitre were trying to get. Because first he believed that he believed strongly in the static principle of space-time, but he also knew that there is a problem underlying it, and he thought like, yeah, probably yeah, there is a solution of his equations, but that doesn't mean that solution is a physical. And he said that this is an unphysical solution. And so differential equations can have physical solutions and unphysical solutions, and probably this is an unphysical solution to have this stuff. So he said like, please do not waste time on this. This is a stupid idea. Again, example of intellectual snobbery, which comes in. Again and again, it slows down a bit the progress of science. So by 1930s, most of the scientific community, which was not intellectually gifted like Einstein, and they were starting to believe in observation, they started acknowledging the expansion of the universe. That yes, the universe is expanding. And at some point, Einstein also gave up once he realized that the evidence is not here. But then it led to many questions and doubts, because it led immediately to the question of how did the universe begin? Because till these things were discovered, there was no such question that how did the universe begin? The answer was the universe is always like that. It is given. And then yes, things happen in it because things just form. The matter just goes from one thing to another. The idea was that as E equivalents to scale suggested, energy converts to mass and so on. These were kind of the ideas that were floating around. That there is a lot of energy in the universe and galaxies just go away and the energy is gone. We should not waste our time on asking such questions. You should be looking at the real questions which are affecting physics. Again, like same cycles repeat each other. But there are always some folks or rebels who want to ask questions which no one wants to ask. But these questions led to a big problem. If you have an expanding universe and if you go back in time, then we know that the universe will contract to a point. And when the universe will contract to a point, the gravitational field becomes infinite, the tidal forces become infinite. And it turned out that Einstein's theory broke down at that point. And this is where Einstein was, I think, afraid to acknowledge the idea. And this leads to infinite bending of space-time, and it destroys completely that space-time fabric. The fabric is completely torn apart. So there were people who were big shots at that time who knew like this is going to mean that Einstein's theory is completely wrong, and for that, and I think this was a big problem for many people at that time, because Einstein's theory was kind of like a great aspiration of human mind, which had taken all the ideas from Machian principle, from Newtonian dynamics, some bits of Aristotelian philosophy, and so on, which led to one this great theory of general relativity. So Lincoln, Sir Arthur Lincoln at that time, who was one of the biggest proponents of Einstein's theory and had discovered the experimental proof for Einstein's theory, he conjectured that these singularities which are being found, where the space-time fabric just rips apart and the gravitational field becomes infinite, these are extremely special cases, and these are not realistic cases, because the way they were found was that for universe which looks same in all directions and is completely homogeneous. And they said, look, this is an assumption. The universe obviously doesn't look same in different directions. The universe is anisotropic. And if you take the universe to be anisotropic, Eddington conjectured that the similarities will be absent. There will be no Big Bang. And he tried his best to find a loophole, which is evident from this quotation. And Eddington was a great philosopher and scientist of his time, and influenced many people who were around him, and this greatly influenced Fred Hoyle at that time. So this is Sir Fred Hoyle, and along with various people, Herman Bondi, Burbages, and Naliker, who was student of Fred Hoyle. Naliker is still alive, and Naliker is the one who actually made that institute where I did my PhD. So they came up with a theory which is called as a steady state theory, which was an extremely popular theory. They said, yes, okay, what is the task? The task is how do we explain what Hubble has seen. The task is how do we explain how do galaxies form. We can explain, and we are going to use essentially Einsteinian ideas, and then there will be a C field, a creation field, which will have a negative energy, and that negative energy leads to these formation of galaxies and so on, which are positive energies. So they had a C field. And they had a perfect cosmological principle in which the universe is not only same in space, but also in time. Great radical idea. And this theory was very successful for about 10 years and was able to explain various things. There were competitors of this theory, and that one of the competitors was George Gamow, who was a Russian physicist who actually was in some way working on understanding like nucleosynthesis, hydrogen bomb, and so on. He knew a lot about explosions, and that is what he was trained on initially, and that is what he used. His idea was that one of his ideas was that he took forward Dimitri's ideas and explored ultra-dense state of matter from which the elements would originate, and he predicted that the universe will have a very cold background radiation, the cosmic material background radiation. So this was kind of the striking difference between the steady state theory, which predicted no background radiation, but explained various other things, and Gamow's theory, which predicted background radiation. And Big Bang, the term Big Bang was actually not coined by Gamow, who was a great physicist. The Big Bang was actually coined by Fred Hoyle. Fred Hoyle was given a BBC interview, and BBC asked him various questions, and this is just the exact quote. And BBC reporter asked a question about it. Well, we have heard about these crackpotish theories which have been talked about by some physicists and so on. And his idea was that these theories were based on hypothesis that all the matter in the universe was created in one big bang in particular time in remote past. And he laughed at it. I have never heard the video recording of that, but that is what is written in those books. That it was done in a very skeptic and in a derogatory this term was used. Like they had a big bang and so on. And then the press started reporting the Big Bang theory. And that is where that word Big Bang became very catchy. But it turns out, again to mention, Gamow wrote many, many beautiful books. And this This is one of a very nice book which he wrote. Mr. Tompkins in paper back there. Mr. Tompkins is a son-in-law of a physics professor, and he goes to his father-in-law's lectures, falls asleep, and then he starts dreaming about, let us say, quantum mechanics with Planck's constant very large, or speed of or the length contraction and time dilation with speed of light very small, and he starts seeing all those phenomena in his daily life while he's dreaming, and he understands physics. So Gamow had a very entertaining way to teach physics, and it's a very beautiful book. So what about similarities? Let's go back to that. So steady state theory was kind of doomed once the cosmic microwave spectrum was found. But at the same time, there were mathematical physicists who were trying to figure out about similarity. So Amal Kumar Rai Chaudhary, he proved Arthur and Newton wrong by taking a model which was anisotropic, like what Eddington has proposed. Okay, take an anisotropic universe and see whether the similarities form. And he showed, yes, similarities do form. And then Bob Garrosh, Sir Roger Penrose, and Stephen Hawking in the 60s, they took all these ideas far further. And they were able to show that similarities are general features of space and time in Einstein's theory. So similarities are there. They are the general features. We have to live with them. And they also tell us that these are the final boundaries of Einstein's theory. So similarities also tell us that Einstein's theory is not the final answer for gravity. If you try to modify Einstein's theory, keeping it consistent with the solar system observations, and again try to study similarities, you will again get similarities. So there is no going away from this philosophy. On the other hand, you also know that Einstein's theory is extremely successful. Like in gravitational wave detection, we have seen that. So we cannot throw things completely away. So why do similarities exist in Einstein's theory? To answer this, we have to understand that we are actually ignoring probably the atomic structure of space. Like if the matter had atomic structure, if the gravity, the Einsteinian and the philosophies we have seen from the very beginning are that the space-time and matter are actually all related, then probably we are just ignoring the atomic structure of space and time. Why do similarities exist? Because we are given that differential equation or partial differential equation, and we keep on dividing terms in that partial differential equation. Then we get a zero in the denominator. Who tells us that that calculus is valid till in the quantum regime when the universe becomes smaller than the size of a hydrogen atom? Like if even for the normal matter, the predictions of the classical theory, like the Rutherford model, or the probabilities become much more kind of trajectory scale, and everything is probabilistic. The same thing must have been happening with the universe itself. When the universe becomes smaller than the hydrogen atom, it's wrong to assume that the classical laws of physics are anyway going to be valid, and the quantum theory is going to play a very important role. So we do not know like what happens to the space-time trap. The problem of similarity arises because we are pushing the assumptions so far. Like in the Rutherford model, we were pushing the assumptions so far, very far. And we have to understand the nature of space and time at extremely small scales, and solving the Big Bang problem requires a matter of quantum level. But this is a very, very difficult matter. Let me try to illustrate why. If you want to marry quantum theory with gravity, we have to start with their basic principles. Quantum world is probabilistic. There are no trajectories. Physics is done without trajectories. Quantum theory, on the other hand, uses Newtonian ideas. Whenever we are studying photoelectric effect of photons, or we are studying the behavior of quarks, deep inside the neutron star, we are assuming that there is a fixed Newtonian background, or even a fixed Einsteinian background, but a fixed background to which these quarks or photons or these atoms don't back react. These are the factors on a fixed state, like in the Newtonian theory. The gravity, on the other hand, is dynamic. The black hole is not a fixed state. The gravity's dynamics of space-time, space-time background cannot be static to correctly understand gravity. Yes, by assuming that gravity, the background is static, we can infer some results, like the motion of Earth around Sun. Yes, we can do it with great accuracy. The motion of particles, motion of Earth. If the Sun is becoming a black hole and you are studying the motion of a big object around a black hole, that cannot be done using the fixed background. So now you are looking at a situation where the universe is becoming small, as if it's going towards a singularity. It's becoming denser and denser. Gravitational force is becoming stronger and stronger. So gravity is becoming more and more important. It's not that the gravity is becoming less important. The gravity is becoming more and more important. At the same time, it's becoming smaller and smaller, smaller than the hydrogen atom, so it's becoming more and more probabilistic. So we don't know how to do these things. We either know how to do physics of quantum theory, like electrodynamics or magnetism, or like on a fixed background, or we know how to do gravity without the background, but we do not know how to quantize. So to quantize, what do we have to do? In quantum gravity, which is this matter, the space-time itself has to become the quantum. In a way, the space-time itself will have its own atomic structure, which will make the space and time, which we look at it, and it will have no background. So it's like saying, yes, the problem is, I like to try to illustrate, like if you are like 50 feet away, if you look at this floor, it will look very uniform, but we know it has tiles built on it. So the problem is not just that figuring out those tiles of space-time, but these tiles had a layer below that, a substrate layer, which was laid down on concrete when this observatory was made. So there is a background. But these tiles of space-time, if you discover, they do not even have a background. So how do they emerge? And where do they emerge from? And how do they lead to? So it's an extremely difficult problem. And it has two main directions. One is called a string theory, which comes more from the side of the standard model of particles and so on, still getting gravity as force. And the second main branch which I work on is quantum gravity, which is less ambitious, which just tries to do this marriage. String theory tries to do the marriage not only of this marriage, but a grand marriage in which all the forces will also come together and there will be a unified theory of physics. Okay, so how do these atoms of spacetime look like? So these are all pretty pictures, but they have, I'm deeply respectful to people who are a decade older than me and 2 decades older than me. They have spent their entire youth figuring out these pictures. These are just pictures, but the mathematics behind these are books which are these thick, which I don't understand most of those things. But like these are theorems and theorems of very deep mathematical results, starting from early 90s till 2005, which have led to these pictures. The idea is that the space and time is actually made up of quantum threads, which loop around and intersect each other, and each thread carries information about how to construct nearby space. So some sort of a free space, which is there. There's no time. There is some sort of a free space which leads to this tile-like structure, which emerges, and the space-time at the Planck scale, which is where the quantum effects become important, as a discrete tile-like structure. These are the building blocks of the space-time, or the atoms of space-time. The picture looks something like this. Most of this work is done by the German group in London, where this video was also made. Basically, the idea is that if you really look, this is an artistic conception. This is not what we have ever seen, but this is what mathematics predicts. That the space looks like this as the geometrical structure, and as we join these things, then these loops form, and as we look from the far away, then these geometries will look like smooth geometries on which the particles will form and so on. If you take this picture into account, this is about space, but then the question becomes, what about time? And the idea is that, well, there is actually no time. If you will talk to even the modern philosophers of science, you will say that time is a construct. And time is always relational with respect to other degrees of freedom in nature. So, for example, as I was mentioning, that whatever is the time on the watch, that has to do with the Earth's rotation around its axis. So you can always figure out a degree of freedom. Let us say a field, like here, like a Higgs field, and then you can take that Higgs field and understand what happens to the volume of the universe. And then you can look at the wave function of the universe, like in the quantum theory. Now you're really looking at the universe as a quantum universe, which is a very quantum object of the Big Bang. So this was a picture which we obtained in like almost 20 years ago now, and like it has been generalized to various complex models, and many groups have worked on it for various results. The idea is that instead of saying that the universe was this big at some time, this plays the role of time. In a way, this field plays the role of a clock. And this is the volume of the geometrical volume of the universe. And this is a small snapshot. The Big Bang is here at 0, where the volume becomes 0. And this is the wave profile of the universe. When you are far, and this was a computation which we later did in LSU in high performance computing using the national supercomputer. And it takes about a month, even on a high performance computer, to do this simulation. Then you start the universe, which is very large. You evolve the universe towards a Big Bang, and you find that the universe is actually following Einstein's theory for an extremely long time. When the universe reaches extremely small size, these effects, which we see, they become prominent, and the gravity fails to be attractive. The attraction of the gravity is actually a property which is only classical. Here the gravity becomes repulsive. Because, and why does the gravity become repulsive? It's easy to see, because if suppose these are the underlying atomic structure of space, the differential equations you have started with, which were telling you, yes, you can keep on dividing, and yes, you will reach a singularity, but division stops. Because eventually you will start hitting these tetrahedra. You cannot divide those tetrahedras. These are the atoms of space here. It's as if like you will have to change your underlying equations of Einstein's theory now, which will stop further division, and then something else will happen. And then what is predicted is that the universe stops going forward towards the Big Bang, because there is no Big Bang in this picture. You cannot divide this tetrahedra beyond a point. And then otherwise there is just a void. And then like the universe just goes back. And it stops dividing and just pushes back itself. So that is what we see in these high performance computation experiments. This is what the underlying theory says. Yes, this can be all wrong. Because this is again a model. This is a simple model. A model in which the universe is homogeneous, the universe is isotropic, the universe is a very simple matter, there are no galaxies in this model. But then later, in a few years ago, we have done it for anisotropic universes, same result. So I would say like the progress is like in 1940s, when singularities were discovered for very simple models. And then somebody discovered in 1955, 54, yes, singularities are there even for more complex models. Now the resolution of singularities is going a very similar path. Resolution of singularity here of the Big Bang was discovered for very simple model. Then it took to almost 15 years to figure out for a slightly more complex model. And I don't know, like hopefully like within the next 10 years we will see it for much more richer model and so on. So these are extremely difficult calculations, and these are extremely computationally demanding calculations, because if you try to take a more complex universe, you'll have to increase the computational dimensions, and then things become very expensive, even for a supercomputer, how to handle it. That is why like the progress is not only mathematically difficult, but also computationally very challenging. So due to the discreteness of space and time, well, with time being a construct, the gravity becomes repulsive. So the picture, which I think the new scientist made, was something like this: that we live somewhere here. Let us say we live somewhere here. If you use Einstein's theory, and if you go backwards, then again, like we're looking at that alternate history of the universe, now the Big Bang will be somewhere here, predicted by Einstein's theory. If all this framework is correct, of what we have learned from loop quantum gravity, and its application, then it's possible that the universe didn't start here, but the universe stops contracting further, and then it goes into the other branch of the universe. The Big Bang is actually replaced by Big Bang. It has various explanations. It tells us exactly how the inflation started. It tells us like how this. It possibly also tells us about the dark energy. So it's not just that it gives the resolution of the singularity, but it comes with some bonuses. How inflation could have worked, what could have caused inflation, what may be the right potential for the inflation, which of the models to pick up, and possibly like whatever happened here is going to influence what happens on the other side, which is the dark energy of the universe. So these are more like recent results, and I'm not going to talk about them. Like let other international groups first verify them, these theoretical findings, and then maybe a couple of years down the line I can come back again and talk about how dark energy is related to this particular bridge here. So the main idea is this, that this was a cosmic microwave background. If you go back into the history, instead of a Big Bang, probably there is a big bounce. This big bounce is the result of the quantization of the geometry, which is there. And the picture becomes complete if everything is if everything holds true. No guarantee if it's going to hold true, but if it is true, then not only we can explain what caused inflation, but we can also, some of my colleagues have been also working on the cosmic microwave background. They have some distinct signature of this quantum entropy. And this is where the most of the research is right now. If these signatures are not found, this model is ruled out. And I think that would be great news itself. Then we can focus on some other problem or try to rectify this model and so on. So let me just summarize. So I believe that Big Bang is an artifact, and it's not just me, like many of the physicists believe that Big Bang is an artifact of assuming that the classical nature of space-time does not change when the energy densities and gravitational field becomes extremely high and volumes are close to vanishing. Like the basic idea is this: if the atomic structure is not going to be described by Rutherford model at the hydrogen atom scale, we are talking about the similarities which are far, far below the hydrogen atom scale, assuming that the classical physics.
So the natural progression through this whole story has been detection, the ability to see something. So where do you think we're heading to either visualize or detect? Because we picked up the cosmic background. We know that's there now, and that has changed how we do this. Where do you think our next big detection is? It dark energy and dark matter? Is that gonna?
I think that's a very important question, but I would like to add something to that. It's not only the detection. It seems like the biggest test actually comes from mathematics itself. It's extremely difficult. It may look easy. It is extremely difficult to make a self-consistent mathematical model. That itself is a first check. Because one may think, well, these are all speculative ideas, and somebody can sit down smart mathematical physicists and sit down and make a new one. It has not happened in the last 30 years. There are two branches and there are two branches. And there has not been much progress even in those branches. So I would first say like to say like when Einstein discovered GR, general relativity, and when Newton discovered his dynamics, Newton was guided with experiment, but Einstein was not, for example. Quantum theory, when it was discovered, was not so much guided by experiments. The probabilities and uncertainty principles were more like theoretical concepts. So yes, but that does not discount anything about it. So couple of things. So first of all, everything is in this cosmic microwave background. Suppose the cosmic microwave background in the next 10 years says everything can be described by classical cosmology, and there is no need for any of the physics of pre-inflation, then we don't know how to prove it. That doesn't mean that doesn't mean that the theory is wrong, but it would mean that one has to be more careful with the parameters of the theory. That's one thing. The second, I think the more interesting thing is about black holes, which I didn't talk about. For black holes, the observable effects are more pronounced, thanks to gravitational wave detection, which are extremely precise and go far beyond what CMB can do. So for black holes, very similar things happen, similarity is resolved, but the physics inside the black hole changes. Since for the black hole, we are not talking about the other side of the universe. We are not talking about what happened 14 billion years ago. We are talking about somewhere near in past, which is manageable in our human time scales. Then for black holes, things are more richer, and I can see that for the black holes, probably the signature would be much more easy to the rule out or detect the model. So both of the things, gravitational wave detection, detection of how the gravitational fields interact with exotic black holes, and cosmic microwave background. All of these in next 10 years are going to reveal a lot of things, or just say, well, yeah, we don't know. Maybe like there are those effects, but these are just hidden, and then these are just theoretical theories. If there was a question here.
Sort of related. I was wondering, as I understand it, there's an observed effect of unknown cause that sort of belongs in the dark energy.
Right.
Okay, good. Does dark energy as a force or as a several different forces that's playing well with this at this point in time?
Not for, not for this. But let me try to phrase the question slightly differently. We don't know too much about dark energy also. We know there is a, dark energy is a phase of accelerated expansion in the present epoch, but we do not know exactly what causes dark. And there is always a talk about maybe the dark energy is given by this phantom field. Like this, or dark energy, in fact, let me try to put it this way. Dark energy is of three types. Dark energy can be because of pure cosmological constant. Dark energy can be by a field like what I was showing in my plot, which rolls down a potential which is called as quintessence, in which the accelerated expansion of the universe will be lesser acceleration than cosmological constant. However, there is also a third type of dark energy, and observations don't rule that out. In fact, observations many years have tried to favor that, where the accelerated expansion of our universe is faster than cosmological constant. If that happens, then classical theory, the classical general relativity will tell that there will be a singularity in the future. The universe is going to rip apart. That's called a big rip singularity. The nature of dark energy will tell the universe will expand so fast that the space-time fabric will rip apart completely. And then if you apply the same ideas of the gravitational field becoming infinite at that, not the gravitational field, but one of its derivatives becoming infinite at that ripping, then quantum geometry can again play an important role. And then these models predict, and we have studied those, that instead of ripping apart, the universe will contract back and lead to a cyclic universe. So there are two questions here. First, whether quantum geometry can lead to dark energy, and that's a huge question, like $1 million question, probably $1 billion question.
So then, say the question again.
Can quantum geometry lead to dark energy? And no one knows the answer to that. No one has even studied those mathematical models. But we have studied those models. Can the nature of dark energy, when coupled with quantum geometry, tell us about the evolution of the universe? What will happen? And then the answer is, instead of this big rip singularity, which Einstein's theory predicts, which is not similar to Big Bang. In Big Bang, the universe approaches a zero size. With Big Rip, actually the universe is infinite size, but even there, just by the nature of dark energy, the tidal forces become, that is the way that it's called phantom dark energy. It's very exotic. The universe will contract back and go into cycles. So it's possible that the universe had a contracting phase earlier, expanding phase, maybe cycles, and so on. But we don't know. These are all mathematical conjectures.
So the James Webb would be helpful with this. I'm just saying it's all, am I correct? It's like Copernicus, you didn't have to observe, you did it all through mathematics. So that what this is, that what has to be here is mathematics and not observation.
No, as I'm saying, like if there are no observations, obviously, like we cannot keep working. The whole point is to find those observational signatures. But yes, James Webb doesn't help quantum gravity observation. There are different kinds of observations which are needed here. It's basically like trying to find the needle in the huge haystack here. And not only that, you have to then make sure that that needle doesn't belong to anyone else, because there are competing models. So not only finding a signature different from the classical theory, but signature finding from alternatives of classical theory. So it's a mathematically, computationally, and observationally very challenging problem.
So theoretical scientists and observational, like all the different, the experimental scientists and the theoretical scientists are working on this?
Yes, I can say that. So one of the things which some of my colleagues are doing is extremely novel, and what they are saying, what they are doing is that, well, we cannot, let us try to make a model of a model. How do we do that? So they are saying, yes, we can discuss about this quantum geometry inside black holes, but let us try to create those black holes or black hole-like analogs, which are called analog black holes in the labs, and they have been making them. And those lead to the physics there is not at the same robust level mathematically right now, but I can see that in the next 10 years probably, the models will be moved out or validated by their own models. So we are looking at the second order models now of analog black holes, which won't have gravity, but gravity-like equations, which you can study in labs. So it's a very rich, very exotic area, all of this. But again, like it's like going in a forest and trying to find out answers. But like most of the people who work in this area, they are quite similar-minded and focused. That we just want to answer what happened to the singularity and so on. And I will be very frank. My training, fortunately, was in an astronomy institute, so I appreciate observation. But some of my other folks, other friends, they don't care. And that is the intellectual snobbery I always warn them that we should not have. And probably whatever we are doing is just wrong. And but that's the way physics works. So I was using that intellectual snobbery as my defense. Yes.
I kind of sort of have a question. So about 20 years ago, I heard a lecture that was talking about, and y'all might need to help me with getting the right probe. So the probe that was sent out, I think it was in 76, probably Pioneer, and I think that's the right one. So it finally reached the outer edge of the solar system, and the lecture was mostly about it crossing the bowway of the solar system into true interstellar space. But then they said to their surprise, from some of the measurements they were getting back from this spacecraft that was built in the 70s, that it was looking like maybe gravity was behaving differently on the other side of the bowway than it was in interstellar space. I was wondering if that relates at all to this, and if it even was kind of proven to be true, or if that's been proven since then.
So I'm not aware of that observation, but I would say that you should not make this suggestion to a purist. Because purists like this tendency, or my friends, some of my friends will just say, yeah, we can explain that. I'm going to just change a parameter in the theory and make it so unnatural, like a Planck's constant in a way, which will explain what you are saying, and probably like I can be in contention of a big prize. So I don't think, so these are all of the effects we have talked about, of these quantum gravity. They all die down, as I was mentioning. If you look at this picture. Quantum effects end here. Like when the universe is like 1,000 times the Planck volume. That's it. The Planck volume is, I mentioned the Planck volume here, right? It was, the Planck density was 10 to the power 93. Planck length is 10 to the power minus 33. So we are looking at 99 in the volume. Something like 10 to the power 90, 10 to the power minus 90 of meters cubed. Quantum gravity effects are dead. Like if you ask someone else, probably he will say no. And I can always have the quantum gravity effect at large scales because he might be interested in doing something else. I'm not going to sell you things which don't exist. So the answer is quantum gravity effects cannot do anything in the solar system or in the interstellar medium. But that is all interesting thing. I'm sorry, I don't know much about it. Is there was a question?
Yes. Early on, you were mentioning that that dark energy and expansion was in more recent, as far as the development of the universe, more recent force or whatever. About what time do y'all think that started kicking in?
Well, I think like I won't know that exactly the time scale. I know in terms of the redshift. But again, like the redshift, I don't know how to. I would say like probably like things would have started 500,000,000 years ago. Rough estimate. Again, depends on the nature of the dark energy, but I don't think earlier than that. Again, it depends on the.
Okay, like then these theories, I've heard some theories where initially there was only one force, not only one type of energy that's split into gravity and the different forces that we know today.
Yes.
Would that get from the expansion? and you were, would that be, the dark energy be something similar to that, there's a force, coming?
That was a hope. Then actually, like my PhD was, that comes from string theory. And my PhD was not in loop one. My PhD was in actually in string theory. And I was then a rebel for my own theory. I changed my religion, at the end of my PhD. I realized that this is not going in the right direction, the way I thought. So the hope was in late 90s and early 2000s, and you see, like, that is the whole thing, right? Like, when I joined my PhD in 1999, everyone told me there is no cosmological constant, it's zero in 99. 2000, 2001. The same professors were telling me there is cosmological constant, and you have to really do your cosmology course. So that is how things change. Fortunately, it has remained like that for the last 24 years. But the point is that the hope of string theory was that we will have this beautiful unification. String theory is a beautiful theory. We will have this beautiful unification of all the forces, and dark energy will emerge. But for the dark energy to emerge, cosmological constant, the simplest form of dark energy, cosmological constant has to be positive. Turns out that string theory is incompatible with the positive cosmological constant. So actually, like, if I don't have Postgres to say it in public somewhere else in a conference, but this is the biggest challenge for string theory, to be consistent with that. Like, forget about, like, even to explain its formation, but like the fact that the universe is accelerating means that the cosmological constant of dark energy has a positive, is repulsive. That is what is needed for the positive cosmological constant. String theory easily gives you negative cosmological constant, but that doesn't give you repulsive force of gravity. That makes it attractive. So it actually makes things short. So it didn't work out. That's it.
All right, I know you have to get out of here, so we're going to cut off any further questions.
If you have any questions, like, my email is very simple: p as in Patrick Singh at LSU.edu, or you can just find Google me, and I'll be very happy to answer any questions.
All right, great. And he's already mentioned maybe coming back and giving us a talk on black holes.
Yes.
I'll come back in fall. Yeah. And then, like, maybe later in fall, and certainly about black holes. Like, that is something really beautiful.
Oh, yeah.
Okay.
Thank you.
Thank you.
Take just a 5-minute break. We'll turn the lights on and stuff, and then we'll do